I'm Sam Foster, and we're going to be talking today a little bit about unlocking some LCMS sensitivity through the use of low flow HPLC. So just a brief outline of what we're going to be going over today. We're a capillary HPLC company. I want to start by defining capillary scale liquid chromatography and a couple of considerations that come into play when you start working at these different scales. We'll take a look at some aspects of mass spectrometry. This is not meant to be a comprehensive overview, but we'll go over a couple of different mass filters and ways that you could perform it. We'll then take a look at ESI, or Electrospray ionization mass spec, and how it changes as we change our flow rate. Then we'll take a look at a couple of real world examples where we've been able to demonstrate our system hooked to mass specs. And finally, we'll wrap it up and take any questions. So for those of you who have been following the series, you'll probably be very well familiar with this slide. This is going over what capillary scale HPLC is. Now, liquid chromatography is primarily broken up into scales based on the inner diameter of the column you're using. So analytical scale, you're typically looking at about a 4.6 millimeter inner diameter column. You can run anywhere from about 1 to 5 milliliters a minute. Solvent saver is 3 millimeters in inner diameter, and narrow bore is 2.1 millimeters in inner diameter. Typically, we'd lump the 4.6 to 2.1 range in fact, there's actually some push now down into about the 1.5 millimeter inner diameter for a lot of these different columns. What we're going to be talking about specifically today, though, is capillary scale liquid chromatography, which is defined as having an inner diameter between 0.1 and 0.3 millimeters. Typically, it's run anywhere from 1 to 10 microliters a minute, so we're talking about a fairly significant order of magnitude reduction in scale. It's also going to have a lot of very interesting properties that we're going to get into, but that kind of sets the stage as to what we're talking about when we mention capillary scale. So there's a couple of key differences between scales. First and foremost, you are going to have significant impacts for extra column dispersion. You're going to have to tailor everything to be much smaller. So with analytical scale, you typically run with flow cells maybe microliters in size. With that, if you're running at a 10 microliter flow cell, that's not normally an issue because you're often running at milliliters a minute. You clear that flow cell in seconds or fractions of a second. If you were to take that same flow cell and run it with the capillary scale, now you're talking about minutes across, which could severely hurt your peak resolution. It'll severely hurt your sensitivity. And so it's a careful balance between how small do I make it and how do I tailor my size and how do I continue to get sensitivity. We have a great explanation specifically on capillary scale detectors and their considerations in our previous installment, if anyone's interested. So detectors and connective tubing are something to be considerate about. Another thing that's really important to mention is that you also are going to get different dilution scales. And this is actually really key as we start to talk about mass spec is you can load the same mass onto an analytical scale column and onto a capillary scale column. And because on the capillary scale, it has less space to diffuse out or break apart, it's going to stay in a much more concentrated band. And in fact, this scales pretty exponentially. If you look at the equation I have shown there, you can see that a 2.1 millimeter inner diameter column and a 0.3 millimeter inner diameter column, so a narrow bore down to capillary scale, if you were to load the same amount of mass onto the column, you'd experience roughly a 40-fold increase in pre-concentration, which is awesome. Now, it's not always the case that that's going to happen. And in fact, you may run into issues where you end up overloading your column. And so this is a tentative guide. That being said, if you can load the same mass onto a column, having a narrower inner diameter is going to typically lead to a more concentrated band. There are matrix effects and all sorts of different things that will change that, but that's the general theory of why we like to go smaller. Now, for those of you who aren't aware, right, we have mass spectrometry as a method of detection. This is a very common method of detection. It's in a lot of labs now. The general idea is to take an ionized gas and manipulate it through a series of electromagnetic fields to separate these ions based on their mass to charge ratio, or M over Z. So what we typically do is we have some source of ionization, some way of introducing the sample into this electromagnetic field. And we're going to go into a couple of methods for that. Then we actually have the electromagnetic field, and there's a number of different types that we've come out with, and we'll go over each one. After that, it's then sent off to a detector, which will collect these analytes of a specific M over Z ratio, count them, and be able to give you an output or a mass spectra. And this is really useful because it's a very high sensitivity detection method. It also can provide structural information, as we'll get into, depending on the type of mass spec. So it's a very useful technique. It's a very sensitive technique. And so it's become very common for a reason. So I think this is probably going to be one of the more common, or in fact, the most common, which is a quadrupole mass spec. In this case, you have your quadrupole, or your 4 poles, as you can see over on the right. What this is it makes a series of oscillating RF frequencies and DC voltages, and it allows you to sort of corkscrew your ions through this quadrupole and separate them out based on their mass to charge ratio. And so it starts at a very low charge ratio, and only analytes of a specific M over Z will be able to make it all the way through that quadrupole into the detector. And then it very quickly sweeps the entire range of analytes, collecting each and every one of them and giving you your mass spectral information. This is pretty great. It's a very commonly used one. It is on the cheaper end. It typically is a little bit less sensitive, and while it can give you a certain mass to charge ratio, it often doesn't provide full structural information, simply because you can't get fragmentation patterns, and so you know what the overall M over Z is, but you probably won't be able to figure out the full structure from it. That's where our second type of mass spec comes in. So this is a triple quadrupole mass spectrometer. In this case, there's now 2 quadrupole mass filters with a collision cell in the middle. And so what this lets you do is you can filter it through the first quadrupole, just like you would with single quad mass spec. Then it has a collision cell in which the ions of a specific M over Z are fragmented and split into daughter ions, and those ions are then filtered through another quadrupole. And so this often gives you much higher sensitivity. It also allows you to get better structural insights. You're able to see not just the overall M over Z, but you're able to see individual fragments, and from that you can piece together what the total structure is. This is often much higher sensitivity because when you're filtering out so much, your signals to noise ratio gets much higher, and it gets much easier to see the analytes you want. That being said, it's often much costlier, and it's significantly bigger just because you have to fit effectively what amounts to 2 and a bit triple or quadrupoles into a single space. And so there are trade-offs when you're going to this. Another one is called a time of flight mass spectrometer. These are often very high sensitivity and high mass resolution systems. In these cases, we're measuring the, as it's named, time of flight. So we introduce ions into the magnetic tube. These ions are shot down this very long flight tube at something called a reflectron. The reflectron is there to kind of invert their speed and send them back toward an ion detector. And so based on the time that these analytes spend flying or going from ion source to reflectron and reflectron to ion detector, you can get a sense of what their ion mass is. So this is a very high mass resolution technique. It is impacted by the length of the flight tube. So you'll often see very high resolution ones have very long flight tubes. This can need this can raise the need to, say, take out ceiling tiles, or in crazy cases, run between floors. But they are a really interesting and really unique type of mass spectrometer. Another one is the Orbitrap mass spectrometer. So this is a sort of newer type. It's on the costlier side. It's a very high mass resolution and very high speed system. In this case, ions are sent in to orbit a central electrode. And as they orbit, they effectively generate a current inside of the electrode. And that current, when you perform a Fourier transformation on it, can be changed into a mass spectrum. It's a little bit technically complicated. They're often very expensive, but they give very high mass resolution, very low limits of detection, and very high acquisition rates. And so they are a extremely powerful mass spec type, but they're often a little bit on the higher end of cost. Finally, we have the ion trap mass spectrometer, and this is sort of a more broad term, as technically the Orbitrap is also considered an ion trap, but the ion trap specifically is a little bit different. In this case, you use oscillating electric fields to hold your ions or trap them. And then based on the changes to these magnetic fields, you can release specific ions as you go through. This typically requires not as high vacuum pressures and can offer good mass resolution. It also allows you to, say, perform cutoffs, so collect all of the ions above a specific point rather than getting specific M over Z values, which is a little bit interesting. They have very small form factors, and they're very useful. They don't necessarily offer the highest mass resolution, although technically, if you count the Orbitrap, they do. But they are still a very unique and very powerful type of mass spectrometer. So I want to pause here for a second. We've talked a little bit about each of the different ways that we can filter these masses, but what we have to do to start with is actually get these masses into the ionization phase. And so what I want to do is I want to put up a poll for everyone to ask, let's see, what types of ionization sources are you familiar with? We're going to go through a couple of these, specifically APCI, ESI, and MALDI, sort of their benefits, their drawbacks, and how they're impacted by capillary scale. Then we will get further into some of these applications. Wow, ESI is winning with 100% of the vote. That's awesome. We'll give it another 1 or 2 seconds. It looks like ESI takes it with 100%. And that doesn't surprise me because electrospray ionization is incredibly common. And we will go over a little bit about why that is. But I want to mention some other aspects of it. So we have what's called APCI, or atmospheric pressure chemical ionization. In APCI, we take the eluent or the effluent from an LC. We nebulize it with a stream of heated gas, which forms these little gas droplets you can see there on the right. Those droplets get fully evaporated before being ionized with a corona discharge needle. And then those the ionized gases are then sent off to the mass spec. Now, this is great for ionizing nonpolar, polar, or pre-existing ionic compounds. It doesn't have as much impact from matrix effects because you're typically evaporating all of the matrix off. That being said, one of the key benefits of ESI mass spec is that you see a sensitivity increase when you get down to these lower flows. You do not see that sensitivity increase with APCI, and we'll get into a little bit about why that is. The next one is matrix-assisted laser desorption ionization, or MALDI. This is a method by which you can actually take some analyte, place it onto a solid surface, and hit it with a laser beam. And this laser beam will excite the matrix. It will send off sort of a plume of hot gas, an ionized gas. And as that matrix evaporates and dissolves, you get left with an ionized bit of your analyte. Now, this is really useful for large molecules. Pardon me. It's typically a soft ionization technique, so it doesn't damage your sample as much. Ooh, pardon me again. However, one of the key differences is that you need it to be spotted onto a plate. And so they have these things called MALDI spotters, where during the continuation of your run, it's not a continual flow. It's something making a bunch of spots onto a tray that are then ionized. And so there's a little bit more to it than just kind of making one connection and moving on. It's still a very powerful technique, and it's still a very useful technique, but it does come with a little bit of an added hassle for the need to perform this spotting onto a tray. Now we'll get to the most popular one, which is electrospray ionization, or ESI. Now in ESI, what you do is you take a small bit at the end of your LC effluent stream. So you typically take a small tapered nozzle and you apply an electric voltage to it. And as you apply this electric voltage, you're typically running with an already existing ionized eluent stream. So you're looking at, say, having formic acid in there or some sort of negatively charged modifier to have the ions sort of pre-existing in solution. When you apply that electric voltage, you form what's known as a Taylor cone, where you're forcing that liquid toward the end because all of those ions want to get away from the voltage through Coulombic repulsion. Now, at the very end of that Taylor cone, the electrical forces overcome the surface tension of your liquid. And what that does is it shoots off a stream of very, very small particles, which we can see there. And these particles have a very high surface charge level, right? They're all extremely positively or extremely negatively charged. And as these droplets fly, they start to dissolve and evaporate. And as they evaporate, it concentrates those charges more and more until, again, they have this decomposition where they split into even smaller droplets, which you can see on the right there. And those, again, undergo a similar evaporation and decomposition. And eventually, at each of these steps, you eject your analyte. And that analyte then is a charged analyte flying through in the gas phase. This is really great for analytes that are able to be ionized through chemical means, things with nitrogen groups that can gain a hydrogen and be protonated or deprotonated. Lots of polar or large molecules are great. Ionic compounds are great, but it doesn't work super well on nonpolar compounds because if you think about something like a hydrocarbon, while you can get it into the gas phase very well, there aren't many sites for it to actually ionize, and so it tends to struggle with ionizing those different compounds. So why is low flow electrospray ionization so good? And the answer is a little bit paradoxical because we think that if you're loading less sample, if you're working with smaller capillary scales, shouldn't you be seeing less sample? And the answer is you actually end up seeing more. And the reason why has to do with those smaller droplets being formed. So when you're running at analytical scale flow rates, you have to use larger inner diameter ESI sources, those needles where it's being sprayed out of. As you go to lower flow, you have to reduce the inner diameter. And as you reduce the inner diameter, you reduce the size of the Taylor cone. And as you reduce the size of the Taylor cone, you reduce the size of the droplets being formed. And so if you're forming smaller droplets, you're going to have quicker evaporation. You're going to have more efficient ionization because you can get those analytes out of the solution much faster. And literature suggests that you can see anywhere between 4 and 10 times higher and sprays, or pardon me, 4 to 10 times higher signals than analytical scale electrospray at the same mass loaded onto the column. And so this is a really powerful technique because you can take the same amount of analyte, load it onto a smaller column, and get 10-fold higher sensitivities. And so this is a really powerful thing, and it's become a staple of the omics community for years because of that. Another really interesting thing, and I'm going to contradict myself in the next slide, is that matrix effects actually have less of an impact. And so what they've found is that at higher salt concentrations, where salt at analytical scales would form something like what you see on the bottom in B there, a very washed out solution, a lot of adducts, and not a whole lot of the ability to see things, as you drop down in flow rate, you actually start to see less and less impact from that salt. And the reason why is because each of those droplets, as they undergo degradation, more and more concentrates the salt. And so the quicker you can evaporate your analyte and get your analyte out and into the gas phase, the less impact from salt that you're going to see. And the technique that releases your salt faster is going to be the one that has these smaller droplets, the ones that can evaporate and eject much quicker rather than having to go through multiple evaporation and ejection steps. And so because of that, as you drop in capillary scale and as you drop your flow rate, your matrix effects actually seem to have less and less of an impact, which is a little bit weird, but it makes sense once you start to look at the ionization process. So a couple of practical considerations. First and foremost, this is a beautiful picture of a Taylor cone right there. As you go to these lower flow rates, you're typically going to be using more and more narrow inner diameters. Because of that, you're going to need to filter better and better because clogging is going to become more and more of an issue. As you go down into even lower IDs, I mean, I've seen low as 10 micron in inner diameter. And so things can get pretty ridiculous pretty quickly when you start to get down into nanoscales. Now, the other thing is because you're experiencing evaporation a lot quicker, you're often going to have to manually set up the source much closer physically to the inlet of the mass spec, just because otherwise you're going to make a more and more diffuse electron cloud or analyte cloud. And so you can't have it as far away as an analytical scale source, and that typically requires a little bit of tuning. I know I just said that salts are better tolerated due to matrix effects, and that's absolutely true, but it should also be noted that salt is still going to build up on your source, and so you need to account for salt fouling. It can be great for analysis and let you analyze things you otherwise wouldn't be able to. At the same time, if you're constantly running high salts with very narrow inner diameters, you're going to experience clogging a lot faster, and so if it's possible, you should always see if you can't optimize your sample prep and reduce the amount of salts. Most of these are things that are going to require experimental fine tuning. There's not really a one size fits all calculation as to direct conversion because it depends on the mass spec, the drying gas, the temperature, the analyte. And so a lot of times it's a case by case basis. The other thing is that you may actually not need specific evaporation methods, and we can talk about that in this next slide. And so again, there's going to be some optimization to it, more so than a plug and play solution. And that being said, let's take a look at some of the applications where we really get to show off the power of the technique. So this is some work that we did with Agilent on some low flow ESI. This was some targeted peptide quantification. And so here we're taking the same mass and loading it onto the column. And what we're able to see is that by switching from a narrow bore, a 2.1 millimeter inner diameter column, to a capillary scale or a 150 micron column, we load the same amount of mass on column, but swap the flow rate from 0.5 milliliter a minute to 2 microliters a minute. And we see up there in the top right, a 10-fold increase in sensitivity between the two scales, changing nothing else other than the flow rate and the inner diameter. And so this is an incredibly high sensitivity increase from changing nothing other than your flow rate. Now, on top of that, we compared it to the Agilent jet stream or the auto jet stream source. And so this source uses a heated drying gas for analytical scale. It's their very high sensitivity source. It also increases the ionization efficiency. However, using that source compared to our system, we still saw a 2 times higher sensitivity. And so this is an extremely powerful technique because analytical scale, even with drying gases and things like that, struggles to come close. Now, on top of that, there are a lot of other benefits. So one of the things that we've been trying to cut down on as analytical chemists is the use of PFAS. PFAS is in everything. It's not great for us. And so there's all sorts of regulations, fears, and guidelines around how to get rid of it. And that's great. And I think we should. The problem is it's really good sometimes for analytical analysis. And specifically, if you're looking at oligonucleotides, HFIP or hexafluoroisopropanol is a very powerful additive commonly used in these mobile phases as an ion pairing agent that not only increases your resolution, but it also increases your ionization efficiency of oligonucleotides. And so if we don't want to get rid of it, or we can't get rid of it, we should at least be trying to use less of it. And so this was another bit of work that we did with Agilent, where we took their standard oligonucleotide ladder, and instead of running it on the analytical scale, we were able to run it on the capillary scale. And while we didn't directly compare the sensitivity 1-to-1, what we were able to see is not only were we able to get the same resolution that we got, but we were able to reduce the PFAS consumption by over 99%. So I believe it was a final 220-fold reduction of total PFAS use for the same sensitivity or better sensitivity on the same analyte and resolution. Additionally, the mass accuracy of the same thing stayed constant. This was a over 100 mer, it was all 103 mer. So very large molecule, not something that you would typically, you know, want to analyze without knowing its mass. Here we put its known mass through the system. We got a nice peak, as you can see over there, and we saw a total mass shift of only 0.2 Dalton. So it was incredibly powerful at analyzing not only these smaller oligos, but much larger oligos, all the way up to 100 mers. Additionally, we measured some real life. These were FDA-approved oligonucleotide treatments. So again, we're able to perform these same types of separations while reducing the total amount of PFAS. And so it's a very powerful technique because you get not only better sensitivity, but it's more environmentally friendly. Additionally, I talked a little bit about the Iontrap mass spec. This is sort of a love of mine, is this compact mass spectrometry. This is a company we partner with called the MassTech. They make the MassTech MTE30. You can see it over there on the right next to the Axcend system. It's a compact and portable mass spectrometer that features a 3D ion trap. It's a very powerful system. It doesn't need external vacuums, it doesn't need external gas supplies, it's fully portable. In this case, we were able to perform a separation of 4 separate benzodiazepines. Here, this allows us for sort of point of need or point of care access if you needed to take it out in a field to analyze, blood samples or get very quick point of need analyses. It's a very powerful technique, and it operates specifically with these lower flow rates because it needs to remain at a lower source. And they have higher flow sources, so I don't want to limit them. But it's a very powerful technique, being able to combine compact LC with compact mass spec and be able to do these in the field types of testings wherever you need for whatever you can think of. Additionally, we also have, and this was some other work I had done with direct infusion using our auto sampler, we're able to continually and directly infuse all the way through a run to perform just automated screening of masses of different samples. Here, I was just doing a screening of reserpine at very low flow rates, down to about 250 nanoliters per minute. This offers a continuous monitoring solution, so you could queue up a number of samples that you may not need chromatography for and still be able to get the same benefits of the low flow ESI without necessarily the need for further separations. So if anyone is interested, we do have a group on capillary scale liquid chromatography. It's open to the public. This is sort of just a group for experts in the field to connect with people who are interested in joining, answer questions, offer thoughts or advice. And so if anyone was really interested today, please feel free to join. We'd love to have you. And with that, please visit our website if you have any questions, or reach out to me, and I will open the floor for questions. All right. Looks like we have a question coming in. Why does ESI benefit so much from lower flow while APCI doesn't seem to have the same effect? Yeah, that's a great question. The answer comes in the evaporation process. So in APCI, you're typically going to be fully evaporated or nearly fully evaporated by the time you reach the ionization or that coronal discharge needle. Whereas in ESI, you aren't going to be fully evaporated. And so a lot of that ionization efficiency comes from the difference in the evaporation process. Looks like we got another one here. How do matrix effects play out at capillary scale? Are they generally reduced or just different? The answer there depends on a lot of factors. Typically, matrix effects are a lot lower when you get to these smaller scales, as we had talked about. They aren't completely gone, and it depends again on your evaporation process, your analyte, and things like that. But in general, and I say that shakily, you're going to see a slight reduction or a reduction. I see another great question here. What are the typical lengths of capillary columns and injection volumes? That's a great question. So I have a full guide, and you can feel free to reach out to me. What you typically are seeing is anywhere on terms of analytical scale. So 5 to 15 centimeters, maybe all the way up to like 25 centimeters if you're doing something like SEC. I've seen monolithic stationary phases that go as high as 2 meters long, but that's much more uncommon. Injection volumes, you're typically on the order of a couple of nanoliters. So 40 nanoliters is sort of our standard injection volume. We can go as high as microliters or as low as about 4 nanoliters. But typically 40 nanoliters or so is about equivalent to what you'd be injecting with analytical scale. And analysis times. Yeah, analysis times are comparable. They're typically 1 to 1. Um, the only places where they may not be is in places specifically with things like SEC, where in SEC you typically have to run a little bit slower than traditionally like reverse phase or things like that to allow the analytes to diffuse through. In those cases, you're going to see a slight increase of extra column, like time in the extra column effects. And I mean, we're talking like 30 seconds to a minute more. We're not talking about very significant. So it's either 1 to 1 or maybe in some very niche cases slightly longer, but not by much. Those are great questions, so thank you. I know who that is. It's great to hear from you. We have another one. If someone wanted to convert an existing LCMS method to low flow, what are the biggest challenges they should expect? I think the biggest challenge is, and we've been talking about converting methods all throughout this series, it's primarily going to be making sure that you have the right source. As I talked about, you have to shrink the inner diameter of your ESI source to account for the reduced flow. And so if you don't reduce that source and you're using an analytical scale source with capillary scale flow rates, you're not going to see much of anything and it's going to be very poor. And so making sure that you have a proper source for the flow rates you're going and that it's properly set up and configured. And there are guidelines for that depending on the source and things like that. And there's not as one size that fits all solution here. But making sure most vendors, in fact, I think almost all vendors have these very low flow sources. And so it's something that you should make sure you have. Another one, do certain mass analyzers benefit more from low flow LC than others, or is the sensitivity gain fairly universal? The sensitivity gain's fairly universal. There are going to be detectors that do benefit more, specifically on ones that are, analyzing very trace amounts, the higher sensitivity detectors or the higher mass resolution detectors. And those primarily because in those cases, you're looking for typically large biomolecules, and you're trying to make sure that you have these very complicated structures and you get your mass exactly right. And so you don't see better sensitivity. It's just that low flow techniques are typically used on certain types, like time of flights or Orbitraps, more than they're used on quadruples. It's not to say that you can't. It's just that that's typically what's done. Are there cases where you'd choose analytical flow over capillary despite the sensitivity advantage? It's a great question. The answer is it should normally be 1 to 1. I can't specifically think of a case where analytical is preferred over capillary. Capillary in general is equivalent or better, and so I wouldn't necessarily be concerned. I mean, maybe if you don't have a capillary scale system, but in that case, you should probably go get one because I think they're cool. But yeah, it's normally 1 to 1 or capillary comes out ahead, except in APCI cases. Then it's just 1 to 1. Have you tried particle beam MS for capillary LC? I have not. That sounds really interesting. Do you have a particle beam MS? I'd love to try. That would be sweet. We should chat. Oh, we should chat. That would be really cool. I would love to get my hands on one. All right. If there are no other questions, I'd like to thank you all for coming. And with that, feel free to reach out if you have any other questions and have a nice day.